everyone, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to teach you Passive Microwave Devices Part 2. So, in this section, we are first going to have the microwave terminations. And the microwave terminations are the precise loads required in the microwave measurement and calibration system. Most common among them are the match termination and the variable precision short circuit. So, the termination are basically provided at the end of any system when we have for getting the exact calculation of something or for measurement of something or for the calibration of something. In some measurement we apply the exact match load, and in some we apply the short circuit load, and when somewhere we have a open circuit. So, in that when we want to measure the in some experiments we want to measure the impedance of something or whether get the, so as per the requirement these terminations are used in the microwave. A matched load or a match termination absorb all the power incident on it without any reflection. On the other hand, a microwave line terminated in a matched load does not have any reflection, and it is equivalent to terminating the line with its characteristic impedance. So, when the system is terminated with its matched load, in that case there is no reflections, or we can say there does not exist any standing wave, or that in that condition the line is supposed to be terminated with its characteristic impedance. The short circuit termination produces an adjustable reactive load at the desired point on the microwave line. So, what the S matrix for a terminations? When there is a ideal short, in that case our S11 should be equal to -1, and for the ideal termination, and these conditions are for one port. Ideal termination S11 should be equal to 0. When we talk about the active termination, that is reflection amplifier, in that case mod of S11 should be greater than 1. For the 2 port network, ideal termination of length L, in that case our matrix should be like this: 0 e to the power minus gamma L, where gamma is our alpha plus j beta, propagation constant, alpha is our attenuation constant, and the beta is our phase shift, and beta is given by 2 pi by lambda. And for the lossless line, mod of S21 should be equal to 1, and these are the condition basically for the general condition, and for the lossless line S21 should be equal to 1. Now comes the microwave phase shifter. The microwave phase shifter are the device that alter the phase of the electromagnetic oscillation at the output of a microwave transmission line with respect to the phase of the oscillation at the input of the line. Because the phase shifter plays a very important role, because as we have already seen in the magic T, hybrid T, or the directional coupler, the output at which the signal has to obtain we will get received by us, and at the point the signal is not received by us depend also only upon the phase difference. The point at which we have a same phase, in that case the signal is received, and whenever there is a opposite phase, in that case signal is not received. So, whenever basically phase shifter plays a very important role if somewhere we want to have the different phase. The phase shifter basically alter the phase of the electromagnetic or signals which are coming out. The phase shifter change the angle of an RF signal so that it does not interfere with the wrong signals. So, basically it is used for this. In this case the ideal phase shifter has a S matrix equal to this one. This is a 2 port. In this S11 should be equal to 0, S12 is equal to e to the power minus j phi 12, S21 should be equal to e to the power minus j phi 1 2 and this is equal to 0. S22 should be equal to 0. And when we talk about the reciprocal phase shifter, in that case phi 1 2 is equal to phi 2 1, while for the gyrator is also one short of a phase shifter. Phi 1 2 should be equal to phi 2 1 plus pi. These are the gyrator. An ideal gyrator is lossless, and in that case S multiplied with its conjugate will give the result as 1, but it is not reciprocal. Gyrators are often implemented using active electronic component. However, in the microwave range, passive gyrators can be realized using magnetically saturated ferrite elements. About the ferrite elements, we will study in our next lecture. Ferrite elements includes many microwave passive devices such as circulator, isolator, and gyrator basically comes in that category also. We can realize the gyrator with the help of a ferrite components, but here it is a phase shifter without the use of a ferrite elements. Now, microwave attenuators. So, microwave attenuators are basically used to reduce the power. As a passive element, those are used to control the amount of microwave power transferred from one point to another in a microwave transmission line. So, in every microwave system, after the signal, in our lab also we can able to see it, that whenever there is a microwave source which is relates to the microwave source from the klystron, and there after that we have a attenuator to reduce the power to particular level. That depends upon, this is a rotating structure basically which we use in our lab. We can rotate that for getting the exact attenuation which we want. So, as per that, the microwave attenuators are basically divided into two types, that is fixed attenuator and the variable attenuator. About this we will discuss. First of all, we will have one more line, some more lines about the attenuators. Attenuators are commonly used for measuring power gain or loss in dBs, for providing isolation between instruments, for reducing the power input to a particular stage to prevent overloading, and also for providing the signal generator with a means of calibrating their output accurately so that precise measurement could be made. Though one thing which we interpreted from this line is that microwave attenuator basically prevent the overloading and also used for the precise measurement of our signal, and the main motto is to control the amount of microwave power which is transferred from one point to another. So, the first thing which we will able to have it, microwave source. In every test bench which we see in our lab is provided with the attenuator, and after that we have a attenuator. So, the signal which we actually receive, that power is reduced with the help of attenuator, so that the other component which are in our microwave system, or we can say in the brief section in our labs, does not get disturbed or will not get overloaded due to the microwave power. So, attenuator is basically used to control that. Somewhere there is a structure, we can adjust the power, the attenuation, ki how much we have to reduce the power. So, as per that we will get the power in the remainder section. So, how much power we have to reduce, divide the microwave attenuator into the two parts, that is fixed attenuator and the variable attenuator. Fixed attenuator means ki what the attenuation the instrument have is fixed, we can't able to change it. If it is able to provide attenuation of 1 dB or the 2 dB and it is in our system, it is fixed. If you want also that we should reduce the power to the 4 to 5 dB, we can't able to do this. To reduce this problem and to remove this problem, variable attenuator comes into existence. Variable attenuator does what? If we want to reduce the power to 1 dB, we can adjust accordingly, and if we want to reduce the power to 4 dB, 5 dB or further, we can adjust power accordingly, and this is basically our microwave variable attenuator. So, this is some of the fixed attenuator structure. They are used where fixed amount of attenuation is to be provided. We are not able to change the attenuation, and once it is installed in our system, it is. If a fixed attenuator absorb all the energy entering into it, it would be called as the waveguide terminator. So, when a fixed attenuator can be called as a waveguide terminator, when it absorb all the energy entering into it, they are called as a waveguide terminator. This normally consists of a short section of a waveguide with a tapered plug of absorbing material at the. This tapering, basically it is a tapered plug of absorbing material, and this tapering is done for providing a gradual transformation from the waveguide medium to the absorbing medium, thus reducing the reflection occurring at the media. Tapering is basically, we are able to see that there is a tapering occur, basically used for gradual transition from the waveguide to the absorbing material. And this is one of the structure of the, there is no option of for us available, we can change the attenuation, it gives the fixed amount of attenuation. Now comes the variable attenuator. So, variable attenuator provide continuous and stepwise variable attenuation. For rectangular waveguide, this attenuator can be of flap type on vane type, this is a vane type, and for the circular waveguide, it is a rotatory type attenuator. So, we can see in this flap type attenuator, this is a flap. We can adjust the flap so as to get the maximum or the minimum attenuation as per our requirement. There is an option for us so that we can adjust the flap according to our will. In this also, this is a slide vane which is adjusted so that to obtain the maximum or the minimum attenuation. We can have the you can able to see this, that this is the condition when we able to get the maximum attenuation, and when this slide, basically this slide yahan exist is at the end, we will able to get the minimum attenuation. So, this things, this is a instrument which are used to get the movement of the slide, and as per the movement of the slide, we are able to change the attenuation which exists in the attenuator. And now comes the rotatory type attenuator. So, rectangular to circular waveguide transition exists here, rotating section of the circular waveguide and the resistive card. So, basically these are used, resistive cards are used for absorbing the microwave signal, and that is why by absorbing the microwave signal, it can reduce the power available in the signal, and thus it works as a attenuator. Now, the matrix of attenuator, the S matrix of attenuator is given by 0 e to the power minus alpha, e to the power minus alpha 0, S11 0, S12 e to the power minus alpha, S21 should be equal to e to the power minus alpha, and S22 should be equal to 0. Attenuation is in Neper, alpha is in Neper unit. Attenuation in decibel is given by this formula, where A is equal to minus 20 log to the base 10 within bracket S21. Now, let us do some numerical related to the microwave transition. So, let us have one numerical. The numerical comes both for all the topics in the E plane T, in the H plane T. Somewhere we have to prove some properties related to the S matrix also for the different waveguides, E plane T, H plane T, magic T, hybrid T, directional coupler. In all that topic, numericals come, and all depends upon the property that we already know. So, for the practice, just for 1 or 2 numericals is available here for you. The signal of power 32 milliwatt is fed into one of the collinear port in a lossless H plane T. Determine the power in the remaining ports when the other parts are terminated by means of a match load. So, what is saying here, the power is fed, this is the H plane T. So, H plane T, whenever we talk about the H plane T, what the thing which comes to your mind, that it is a 3x3 port. Okay. And when a power is given to one arm, other is thing 3 port, 1 and the 2, and the third is the H. Power is given to port is third arm, it will transmit it to port 1 and 2 equally and in the same phase. So, keeping this in mind, we are able to have this. What we are saying, that the signal of power 32 milliwatt is fed into one of the, that means it is fed into the one of the collinear arms, that is either into the 1 port or in the 2 port. So, here we are assuming that power is fed into the port 1, that is 30, and it is equal to 30 milliwatt. It is not fed into the port 2 and the port 3. If you can able to say, you can also take A2 as a 32, it depends upon you, and here I am saying that I have taken A1 is equal to 30 milliwatt. Now, we have the matrix of a H plane T here, B1 is equal B1 by B2 B3, and here it is the H plane HT matrix, and here A1, A2 and A3. So, here we have assumed that A1 is equal to 30 milliwatt. Now, if we want the B1, in that case what we will able to do? What we have? 30 your A1 plus this 0, this 0, which is our A2 and A3. So, what we have here? This will be 8 milliwatt. Okay. This is our power output available at port 1. Now, similarly for the B2, A1 which is our 30, this 0, this 0. So, again it will be 8 milliwatt. Now, for the B3, zero zero, what will we have? Half into this is 32. So, this will be 16 milliwatt. This is the way we are able to solve the numerical related to the H plane T and the E plane T. E plane T also the this type of numerical come, magic T also this type of numerical come. So, you should remember the matrix which we have in the process of solving this numerical. So, in this it is asked to calculate the determine the power in the remaining ports. That means, we have to calculate the power in all the ports because this is the incident. So, we are able to get the power, that is B1 is equal to 8 milliwatt, B2 also 8 milliwatt and B3 is equal to 16 milliwatt, and with the help of the matrix which are available to us. Now, comes the numerical 2, and it is based on the directional coupler, and what is been asked in this? 90 watt power source is connected to the input of a directional coupler. So, what is power? We have a waveguide like this. We have a, basically it consists of a 2. somewhere it is 3 mentioned here and somewhere here, it depends upon the. So, what we have, this is the coupling port and this is the isolated port basically, and power is given to this one, this will be P1, and it is the here we will get the thorough output. So, a 90 watt power source is connected to the input of a directional coupler, that means P1 should be equal to 90 watt. With a coupling 20 dB and directivity is equal to 35 dB and an insertion loss of 0.5 dB. Find the output at the through, coupled and the isolated port. This is the through output, this is the coupled output and this is the isolated output. So, you have to calculate the power, output power in all the remaining 3 ports. So, for that what is going to be have here? C, which is our coupling factor, is equal to 20 dB and directivity is equal to 35 dB. So, C is equal to 20 and it is equal to 10 log to the base 10 Pi upon the Pf, and what is Pf here? This is our third port. So, we are going to solve it. For this what we do? First of all, 10 log to the base 10 Pi upon Pf and it is equal to 20 upon 10 and it is equal to 2. Now, I am taking this 10 here also only. Now, for getting the Pi upon Pf, it is equal to, this base is 10, that is why 10 here, 10 square, that is equal to 100 now. Pi upon Pf is equal to 100 and what is available with us? Pi is available with us and we have to calculate Pf. So, what we will do? We will write Pi is equal to what it is given in the numerical here, that is equal to 90 watt, and so what we are going to have? Pi is equal to 90 by Pf is equal to 100. So, if we want to have the Pf, we will have 90 upon 100. Now, you are able to get it, 90 upon 100 is equal to 0.9 watt, which we are getting here. So, coupled output is equal to 0.9 watt. So, I am writing here coupled output 0.9 watt. Now, we are going to solve the other one. Now, the directivity D is equal to 35 dB and it is equal to 10 log to the base 10 Pf upon Pb, which is our 10 log to the base 10. Pf we have already calculated here, which is equal to 0.9 dB. So, 35 dB. So, first thing, log to the base 10 Pf upon Pb is equal to 35 by 10 is equal to 3.5. Now, Pf upon Pb is equal to 10 to the power of 3.5. To the power of 3.5 and you have to calculate this, and now Pf 0.9 watt, Pb is equal to 10 to the power of 3.5. I think now you are able to calculate the Pb. Pb is equal to 0.9 watt upon 10 to the power of 3.5. You are required to just solve it and you are able to get the value of Pb. So, here we have get the value of Pb at, by doing this, 284.6 microwatt. 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 So, 284.6. Isolated port PB, 284.6 microwatt. Now we have to go find out the power at the throw input, that is our port 2. Now, received power is equal to Pi minus Pf minus Pb. We know what is our Pi. Pi is 90, Pf 0.9, and this is 284.6 into 10 to the power of minus 6. By solving, PR is obtained as 89.09 watt, and then we convert that into the dB, and by converting this into the dB, we get it as a 0.044 dB. And another thing, this will be our output at the port 4, that is our through output, but our insertion loss is mentioned here. Insertion loss is 0.5. So, getting the through output, what we have to do? We have to receive, subtract this 0.44 minus 0.5 dB, and after that we are getting minus 0.455 dB. If the insertion loss is not mentioned, you can directly have this as our power at the throw output, but insertion loss is mentioned, that is why we have to minus it, subtract it, and after that we are getting minus 0.455 dB as our throw output. So, minus 0.455 dB. So, here completes this numericals related to directional coupler. Thank you for attending today's lecture.